So, a couple of things. So, your test grades are in, your journal grades are in, and the quizzes grade is in. Now, if you're upset about your grade right now, don't worry because remember, since my class is point based, right now there's not a lot of points. I still got to go in and add all your Delta Math grades, and that will raise the total number of points. So that means that things will start counting less and less. All right. So, in other words, your grades will go up. And I'm doing those Delta Maths this afternoon. All right. So, if you've been doing your Delta Maths and you have decent grades for that, I'll put you in this afternoon. That will definitely raise your grade. All right. Now, on Monday, I'll tell you how we do test corrections because I told you guys I do offer them. I'll go over that procedure on Monday. All right, so don't worry about that right now, but just know I do offer test corrections because some of you did great, but a lot of you not so great. All right, and again, it's the first test that usually happens. Most people usually suck on the first test. Now you know what to expect. All right. All right, so this unit. So we talked about functions on the last unit. Now we're starting to get into specific types of functions. So for this unit, it's going to be exponential and logarithmic functions. Now, exponential functions you have seen before back in Math 1. You've seen at least the basic versions of them. Logarithmic functions, that's going to be new. All right, but we won't get to logs until a little bit later in the unit. So today what we're going to do is we're first going to discuss just basic exponential graphs and review just basic exponential facts. All right, so we're going to start with that very first journal entry. Now, the reason I made you guys fill out that power chart is because when you think of the word exponential, what do you think of? Exponents. Well, guess what that power chart covers? Your power chart covers. Oh, son of a. Your power chart covers all of your basic powers. All right. So, in other words, this is how you read it. So, the top is your base. The side is the exponent that you're raising that base to. So in other words, 2 to the negative 2 power, 2 to the negative 1 power, 2 to the 0 power, 2 to the first power, 2 to the second power. All right? And underneath is what you get. If you were to put that in your calculator, that's the number you'll get. So you'll see 2 squared is 2. Why did I say 2? 2 squared is 4, 3 squared is 9, 16, 25, 36, so on and so forth. All right, this is going to help you because, again, exponentials, you'll be dealing a lot with exponents. All right, so now, do I expect you to memorize this chart? Absolutely not. But are there some that you do need to at least be familiar with? Absolutely. Obviously, you need to know that anything raised to the 0 power is 1. You need to know that anything raised to the first power is itself. And I highly recommend that you start at least memorizing your perfect squares because you'll be seeing those a lot. So I usually say it's only up to 100. It's only up to 10, but honestly, you should know up to at least 15. So that would be 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. 121, 144, 169, 196, and 225 in that order. All right. Now, you also have your cubes. I recommend with your cubes, you at least know up to 5 cubed. All right. And then the rest, the others, the biggest one is probably knowing if the base is 2, what all the exponents are. And base of 2 is easy because whatever the previous one is, you just multiply that number by 2. That's the next one. All right. So like how 2 squared is 4. Multiply that by 2, you get 2 cubed, which is 8. All right. So hold on to that power chart because it will come in handy as we get deeper to the unit. So if you didn't finish filling it in, Make sure you do that at some point. All right. And the key's posted in the OneNote, but I'll also have it posted in the key page on Canvas. I just got to finish updating that. All right. So the journal entry. So these are graphs of exponential and logarithmic functions. We're only going to focus on the exponential today. All right. So we're only going to focus on exponential, not logarithms. We'll come back to logs. Now, the reason that exponential and logarithm graphs are grouped together anyway is because they are actually inverses of each other. So we talked about inverse functions in the last unit. What does it mean for two functions to be an inverse of each other? They're the opposite of each other. They undo each other. That's what exponential and logarithms do to each other. So an exponential undoes a log undoes an exponential. All right. Now, with exponential graphs, there are some key features that you need to know. So this is the generic exponential function. So where A is always going to be your y-intercept, B is always going to be your base. It's also known as your common ratio. And x will always be in the exponent. If x is not in the exponent, it is not an exponential function. That's why it's called exponential, because your input is actually in the exponent. Now, there are two key types of exponential functions, exponential growth and exponential decay. All right. You have seen at least the basics of them before. So, if I look at these graphs, which of the two do you think is exponential growth? The top one. So, this top one is exponential growth because if you go from left to right, you start low and then you get high very quickly. By the way, exponential and logarithms, if you ever want to know how they connect in the real world, exponentials is used pretty much every day. You see it a lot with banking, you see it a lot with population studies, you see it a lot with anything dealing with money. All right, so if you want to know where it comes into play, you start dealing with interest rates and everything else, exponentials. That's how they calculate them. And if you notice how they get high pretty quickly, that's why interest rates will screw you over, especially if you have credit card debt. All right. Just a little something to know for the future if you think about getting credit cards. So this is exponential growth. Now, the way you know it is because the graph is increasing. Another way is that your B value is going to be greater than 1. So your base will always be greater than 1. If the base of your exponential function is greater than 1, it's going to grow. Now, that means the bottom graph is the decay. So that means it starts high and then it gets low really fast. All right. So this is exponential decay. We know it because it's decreasing. Now, the base for an exponential decay is going to be between 0 and 1. So if it's between 0 and 1, what type of number is it? It's a fraction. So in other words, the base is a fraction. And I mean a true blue fraction, like numerator smaller than denominator. Yeah. Here, I'll zoom out a little bit. Now, another thing to note about exponential functions, they have something called an asymptote. All right. What that means is that it's just a line, whether it's horizontal, vertical, slanted, whatever, that it does not cross. The graph physically does not cross it. All right. So, in this case, exponential graphs only have horizontal asymptotes. So if you notice, this graph doesn't look like it's going past the x-axis. That's because it will get infinitesimally close to 0, but it will never actually cross at y equals 0. Same thing with the decreasing graphs. Has the horizontal asymptote at 0. It would get infinitesimally close to 0, but will never actually touch it. Nope. Because what happens is that it will keep getting smaller and smaller, like the decimal places will keep adding on and on and on and on, but it will never actually hit wherever the horizontal asymptote is. So in this case, it would be 0. So it would be like, you could have like 0.000000001, but you'll never actually have 0. All right. So again, they have horizontal asymptotes. Helps if I could spell horizontal correctly. And typically you write the horizontal asymptote as y is equal to some number. Guys, if you finish your test, just put them on my desk. All right, so now let's actually look at some exponential graphs. So I'm going to use Desmos for this. You do not need to pull it up if you don't want to. I'm just going to pull it up just so you have something to reference. But we're going to focus on graphing these two tables on the left side. All right, so first, we're going to make a table. Now, this is where that power chart will come in handy, because if the function that I'm graphing is to the x power, what do you think I'm doing with that x values that they gave me? So what do you think I'm going to do with my x values to get my y values? Plug them in for the x right here. So all these powers are on that power chart. So what does your power chart say 2 to the negative third is? So what's 2 to the negative third power? It's on your power chart. Wait, actually, no, it's not. Okay, but we can kind of confer what it is. Because what's 2 to the negative 2 power? Negative 3 is 1/8. This is 1/4. What about 2 to the negative 1? 1/2. 2 to the 0? 2 to the first? 2 squared? 2 cubed. So just to note, guys, 2 to the negative third, if you remember your exponent rules, that's the same thing as 1 over 2 cubed. All right? And that's the same thing for any negative power. You take that negative, you put it on the other side of the fraction bar. So basically, you're just doing 1 over whatever the cube, fourth, squared, or whatever is of that number. Now, let's go ahead and graph these points. So, negative 3 to the 1/8, I'm going to get like really, really close to 0, but not quite. Negative 2 to the 1/4, I'm going to go a little bit higher. Negative 1 to the half, so I'm going to go about halfway. 0, 1. 1, 2. 2, 4. And 3, 8. Oops. So my graph's going to look something like this. Now, notice how I'm not crossing the y-axis. All right, that's because it's going to have that horizontal asymptote. But just to be sure, we're going to graph this in Desmos, because Desmos will actually you be able to see where the asymptote is. All right, so I'm going to graph in Desmos y equals 2 raised to the x power. Now, if we zoom out a little bit, it looks like at some point the line is almost on top of the x-axis, but it actually doesn't cross. So watch this. If I go way over here and I zoom super far in, so I'm like in the negative hundreds. I'm zooming incredibly far in. I mean, I'm zooming to death in there. Okay, let's do this. So if I zoom in a whole lot, all right, look right here. So I just zoomed in a whole lot, but look, here's the x-axis, right here, this black line. That's y equals 0. Here's the graph. Is it actually crossing? Nope. So even though it looks like it is, it's actually not. Now, we'll talk about later how you actually find asymptotes and how they develop with the functions, but just know for right now, typically in a very traditional exponential function, the horizontal asymptote is typically y equals 0. That's where it is for its parent function. All right. So if you want to do it that way, its parent function, the horizontal asymptote is usually at y equals 0. So that's the horizontal asymptote. And I'm going to go ahead and graph that on my graph. Just do it as a dotted line across the x-axis. Now, what do you think the domain of this function is? So go from left to right. What's my smallest x value? If I have a arrow going on forever and ever, what's actually the smallest x value on the number line here? Negative infinity. Good. Now, it goes all the way up forever and ever. So it's keep on going to the right forever and ever. It'll circle the world 50 billion times and it'll keep going. So what's the highest x value? Infinity. So in other words, if it's going from negative infinity to infinity, what is the domain? So that's the domain, but what's another name you can call it? All real numbers. So you can also write this as all real numbers. So the shorthand is just an R with a line through it. Now, that's the domain. The range is a bit different. So, what do you think the range is? So if we go from bottom to top, what is my lowest y value? From bottom to top. Or what's it really close to? Not 1. 0. So, we say 0 because, like I said, it gets infinitesimally close to 0, but it never actually touches it. So we're still going to say 0 just because we're not going to say 0.0000000 infinitesimal number 0 is 1. All right? So, but what notation will we put with the 0? The bracket or the parenthesis? It doesn't actually cross at 0. You put a parenthesis. So, its lowest number is 0. Now, what's the highest value? Infinity, because it's going on forever. So, another way, guys, please stop talking. So, another way you could write this is y has to be greater than 0. So, your y values are greater than 0. All right. Now, for the second one, all right, so we have 1/2 raised to the x power. Okay, for time's sake, I'm just going to give you what your y values are. All right, so in reality, it's actually the flip of to the x power. So instead of starting with fractions, you're actually starting with the big numbers. So 1/2 to the negative 3 is 8. 1 half to the negative 2 is 4. 1 half to the negative 1 is 1. 1 half to the 0 is 1. Oh, wait, not 1 half. This will be 1 half. No, why am I saying 1? Oh my God. Guys, it's Friday. I hate myself. There you go. 2. All right. So 1 half to the negative 1 is 2. 1 half to the 0 power is 1. 1 half to the first is a half. To the second is a fourth. And to the third is an eighth. And again, you could put this in your calculator and it'll give you the exact same thing. All right. It's not, yes. Yeah. Now, I'm going to take these points and I'm going to graph it on the same graph. So I have negative 3, 8, negative 2, 4, negative 1, 2. Oh, crap, did it move? Yes, it did. Guys, hold on. My computer did a little stupid. There it goes. All right, so I got negative 3, 8. Put that at negative 4. Oh my God. Negative 2, 4. Negative 1, 2. 0, 1. 1, 1 half. 2, 1 fourth. And 3, 1 eighth. So my graph's going to look something like this. So this graph is y equals to the x. This graph equals y is equal to 1 half x. All right, I'll give you guys a minute to finish drawing that. Let me just refill this chart. Yeah, typically just because it's not always necessarily. If the fraction's by itself, then no. But let's say there was a number outside of it, then yeah. A lot of times they do put it in parentheses, though, just so you know that x is just connected to like the 1 of the fraction. So that's 8, 4, 2, 1. All right, everyone good? All right, so let me ask you guys this. Now that we've graphed everything, do you think the purple graph, which is the one we graphed first, do you think that's going to be an exponential growth or decay? The purple graph. It's a growth. If you go from left to right, it starts low and then it gets high. The green one is decay. So the green one is a decay. Now, does that actually go along with what we said on the previous page? With what the b values are? Was our b value greater than 1 for the growth? So in other words, the number connected to the exponent or the x, was that greater than 1? Is 2 greater than 1? Yes. For the decay, is 1 half between 0 and 1? Yes. So that's why. All right. Now, last thing for this one, and then we'll move on to something else. Horizontal asymptote is still going to be at y equals 0. All right. And again, we'll talk about where that comes from later. But domain, if I look at this graph, the green graph, what is my lowest x value? So think left to right. If there's arrows on the end, what's my lowest x value? And negative infinity. All right. What would be my highest x value? infinity. So in other words, all real numbers. I don't really care which way you say it as long as you say it in one of those ways. You can either tell me all real numbers or from negative infinity to positive infinity. I don't care. It's the same thing. What about the range? What's the range of the green graph? What's the lowest y value? 0. Would I put a bracket or a parenthesis? Parenthesis, because it doesn't cross at 0. What's the highest y value? Infinity. It goes on forever and ever. Or it goes up forever and ever, I should say. Now, remember, the other way you can write this is y is greater than 0. Now, what do you notice about the two domains and ranges between the two graphs? What do you notice about them? So, are there any difference between the two domains of both graphs? Guys, come on. I know it's Friday, but I gotta get through this. We're already behind as it is. So, are there any difference between the two domains and ranges? No. All right. Why do you think that is? So let me ask you this. Does the domain and range in this case really matter whether we start increasing or decreasing? No. And since they're both above y equals 0, then the range shouldn't matter either. All right. But if your range if your domain is all real numbers, then it doesn't matter whether you started low and got high or vice versa. All right. Okay, so that's just the basis of the graphs. And by the way, a way you can find the range, every exponential graph, the domain will always be all real numbers. So this is for every exponential. For the range is whatever the horizontal asymptote is. So you start the range at whatever the horizontal asymptote is. So I'll call that y, and it's always going to go to infinity. So our horizontal asymptote in this case was 0. Then that means that's our lowest y value because it doesn't cross. Now, there are cases where it flip-flops and you start from negative infinity and go to 0, but we're not really going to mess around with those. All right, so we're going to put the journals away for right now. Take out your packet, go to the very first page. Yes. Well, put your name on the board because I have someone out. Also, you may want to pull up Desmos on your Chromebooks. You're going to want this for this next part. All right, so guys, if you keep talking like this, I'm just going to rearrange the seating again. So if you want to have a seating chart on Monday, keep at it. That's all I'm going to say. All right, so what we're going to do now is we're just going to review some of the very basic exponential stuff that you guys technically learned back in Math 1, but we all know it's been probably 2 years since you've taken it, so we're just going to review the basic stuff. All right, this is specifically with finding things about its graphs, so like y-intercept, things like that. All right. So first, before we even do anything with exponential functions, we're first going to review exponent rules. So this first rule is the power rule. And all it states is that if you have a power raised to another power, so this is the 6th power raised to the 3rd power, all you do is multiply the exponents together. So if we distribute that 3 to the 6, what's 3 times 6? 18. So this will be n to the 18th power. And that's it. That's all it is. So in other words, you would distribute the power to every base. So let's say there was like a 3 in front of this n. I would also distribute the power of 3 to 3. So it would be 3 cubed into the 18th. And 3 cubed is just 27. All right, but that's just an example. Now, the next rule that you'll see a lot is the product rule. And all it states is that if you have like bases, and by bases, I just mean whatever's connected to the exponent, not necessarily a number next to it. So you're multiplying like bases. All you have to do is add the exponents. So for example, you guys know x times x squared is x cubed. Technically, you're adding 1 plus 2, which is 3. All right. Now, numbers, you just multiply like normal. So what's 10 times negative 10? Negative 100. Now, these are my like bases because they both have a base of x. So this is the same thing as negative 100 times x to the 4 plus 5. So my answer would be negative 100 x to the 9th. Now, that was just some simple exponent rules that we just had to review very quickly. All right. Now let's get into the exponential stuff. Now, something you need to know about exponentials. All right. You need to know the basic formulas for growth and decay. So I would write this somewhere where we have space. The formula for exponential growth is A is equal to P times 1 plus R to the T power. Where A is equal your accumulated. So basically after whatever time period it was, that's how much accumulated. P is your principal. And principal is just a fancy word for saying what you started with. It's mainly used with money. So, in other words, let's say you started a savings account and it had a 5% interest rate. All right. Basically, your principal will be however much money you initially put into that savings account and then you left it alone, didn't touch it. All right. And then A would be however much time passed, that's how much money you currently have in your account. So that's principal, that's just the starting point. R is your rate. Now, it's typically given as a percentage. So make sure you convert it to a decimal. So you've got to convert the percentage to a decimal. And T, of course, is time. And typically that's in years. Typically. Not always, but typically. Now, decay is pretty much the exact same formula, except you switch out that plus with a minus. So it would be A is equal to P times 1 minus R to the T power. And all the variables mean the exact same thing. Now, deciding on whether you use the growth or decay formula just depends on what the problem states. So in other words, if you're gaining money, you're appreciating, meaning you're growing. If you are losing money, you're depreciating or decaying. All right. So it's just little words like that that help you determine which formula you use. And again, the only difference between these two formulas is one singular sign. One has a plus, the other one has a minus. So let's look at this first problem. We're just making the formula. So Ella has a collection of vintage action figures that are worth $430. The collection appreciates at a rate of 4% per year. Which equation represents the value of the collection after 7 years? So before we do anything, let's actually establish what all of my variables are. So A, P, R, and T. Now, A is how much it's worth. So they're using V as A. What's my principal? What did she start with? Or how much did she initially spend on them? $430. That's what she initially put into it. So your P would be $430. Now, how much is it growing? 4%. Now, what's 4% as a decimal? 0.04. So if you don't know how to convert percentages to decimals, all you do is just take that number of the percentage divided by 100. Because every percent's out of 100. Finally, how much time do they want to pass? 7 years. So all we got to do is just use these, plug it into the proper formula. And which formula am I plugging in, growth or decay? Growth. It's definitely growth. What word clues me into growth? Appreciates. That clues us into this being a growth problem. So I'm just going to plug in my equation verbatim. So I have V is equal to 430, which is my P, times 1 plus 0.04 raised to the 7th power. So that's the equation. I haven't done any simplifying yet. But really the only simplifying you need to do in this case is just add those together. So what's 1 plus 0.04? No. 1.04. So V is equal to 430 times 1.04 to the 7th power. So which of these answer choices matches either the purple or the red? No. I mean, which answer choices matches either one of these? B. Now, why does D not work? What's the difference between D and the purple equation? Right, it has that negative instead of the positive. So be careful like that. They like to throw stuff at you like that. So, knowing what you know now, try number 4 on your own. So set up the equation, try number 4 on your own. I'll leave this up for your reference. All you're doing is, guys, hush. I should not hear any talking at this point. All you're doing is plugging and chugging into the formula. So figure out whether it's going to be a growth or decay, identify your different parts of the function, and then plug it into the formula. Now, when you're picking your answer choice, you may have to simplify what's in the parentheses, like do the addition or subtraction. So if you need to do that, make sure you do. It's not the first time I almost died by a wire book bag. All right, thumbs up if you're ready. Give you guys one more minute. Yeah. All right, let's go over this. So, A, P, R, and T. Right. Son of a. Son of a is. I didn't finish that sentence, so I did mean it. All right, so now for A they use P because for population. What's your principle? So how big was the population when they first accounted for it? 130,200. So that's what your P will be. What was your rate? So your rate was initially what? 5%. And what is as a decimal? 0.05. And how much time do they want to go by? 6 years. Now, is this going to be a growth or decay problem? It's a decay. What word clues you into that? Shrinks. It's getting smaller. So we're using the formula with the minus in it. So it should look like P is equal to that big number that I don't feel like saying. All right. Now, that means your answer is D because they didn't simplify it, but it is the correct answer. Now, if you did simplify it, you would just do the subtraction on the inside. And it would be 0.95 to the 6. Now, here's my question. We know it's a decay problem, meaning it's decreasing. Is it not true that our base, which is right here in the parentheses, is between 0 and 1, which we know to give us a decay graph? Is 0.95 between 0 and 1? It absolutely is. All right, that's why it's decaying. Whereas our previous problem, our base was 1.04. Is that greater than 1? Yeah, it's greater than 1. It's slightly greater than 1, but still greater than 1 nonetheless. That's why it's growing. All right. Now, that was just some simple growth and decay problems. Now, let's look at how you can find the exponential equation from a table. And I'm not even going to bother trying to teach it to you by hand. This is a Desmos problem. Okay? So, you know that it has to be an exponential function. So what we're going to do is we're going to put this table in Desmos. And then we're going to do an exponential regression. Now, what a regression does is that it takes points and it fits a function to those points as best as it can. Now, since they want an exact function, this should give you the exact function. If the regression perfectly makes a exponential function, it will line up perfectly. All right? So, we're going to do this together. So how do I input a table if I don't have anything in here yet? We hit the plus key and then table. Now, I want to type in all the numbers. So it's 0, 2. What's the next one? I just don't have it in front of me. 3 and 4. Is that what the other one is? Okay, that's it. Okay. Okay, what is? It's okay. I'll just put the 1 in there. It doesn't matter. It really doesn't matter the order. It really doesn't matter the order. All right. Now, what's the y values? So what's for 0? What's for 1? 6. What's for 2? 3. All right. So if you look, if I zoom out a little bit, all the points are there. All right. Now, I wrote the table out of order. That was my bad. Typically, you'll put it in order because I skipped a number I didn't feel like deleting. Okay. Now, if you see these points right here, what we're going to do is we're going to fit a line to these points, and Desmos does it very nicely for you. So, does everyone see this little symbol that has like a line and then some points off to the side? That is the regression key. And even in the NC version of your Desmos, so the one you'll see on the EOC, this key will also still be there. So what you're going to do is you're going to click that key, and this will pop up. Now, what type of regression is it currently? Linear. What do I want? Exponential. So I'm going to hit the drop down, and I'm going to click on exponential. I'm going to make sure log mode is on if you're using regular Desmos. So if you're using regular Desmos and not the NC one, yes, make sure log mode is clicked. That's why I typically say use the NC one because that's the one you're going to see on the test. So what I did, guys, listen, I'll do it again. What I did is I had the table in. You guys see this key with a line and a couple dots around it. So all eyes on me right now. Come on. You guys see this key with lines and dots all around it. I click that key. All right. This pops up at the bottom then. Currently it says linear regression. That's the default. I want exponential. So I'm going to click the drop down and hit exponential. Make sure log mode is on if you're using regular Desmos. If you're using the NC one, which I highly recommend you do, log mode's automatically engaged. All right. And guess what? There's our function. So our function is y is equal to 2 times 3 to the x power. And all we did was plug in a table. That's why I said easy peasy lemon squeezy. So try number 6 on your own. See if you can get that function. You mean you can't plug in your Chromebook into the thing that's dead behind you and have it out at the same time? Guys, this is a no talking affair. Your lips do not need to move for you to put a table in. Yes, sir. Put your name on the board because I have someone out right now. Mm-hmm. Hold on. If you're using regular Desmos, like if it has a little log mode check off, make sure it's checked off. once you have that equation, write it down on your paper. By the way, you can use this trick if you have to find any equation from a table. Depending on what they ask you to find. If they want a linear function, use a linear regression. If you want a quadratic function, use a quadratic regression. If you want a cubic, use a cubic regression, so on and so forth.
Is exponential regression?
Anything that's on that drop down is your regression.
So she was on the
Basically.
or that she was supposed to teach that in her math. Well,
All right. Shh, shh, shh. Okay, what'd you guys get as your equation? Yep. Raise to the x power, yes. So, I put it in Desmos, the exponential regression, there's my function. How'd I get what? All right, so like I said, if you need to find any regression on here, most of the ones that they would ask you to find an equation for is in this regression table. All right, so that strategy can be used for pretty much any type of function. So it was 0.02 times 0.5 to the x power. All right, now back to growth and decay. Let's do some very basic calculations. All right. So now we're actually going to be doing some evaluating. So we're going to put it in the formula, then just throw it in our calculator. Yeah. Write your name on the board because I have someone out. So let's work through this. So $7,800 is placed in an account with an annual interest rate of 6.5%. How much will be in the account after 29 years to the nearest cent? First off, is this going to be a growth or decay? Growth. How do you know? Well, if you place something in an account, won't it obviously grow? Yeah. Well, it will actually grow. So if you've ever looked at a savings account, what happens is that if you ever see something called interest payment, that's the bank actually adding money into your account, because if it accumulates interest is actually money that gets accumulated into your account at whatever rate it is. So they take however much is currently in that account, then take, like, for example, 5% of that money, and they add that back to your account. So for example, let's say I had $100 in my account with a 5% interest rate. What they would do is they take 100, take 5% of 100, so that's $5. All right. And they would take that $5 and add it into my account. So I now have $105. That's how interest works. And then they would do it again. So they would do 105, take 5% of that, add that amount to my account. That's why interest is very nice. And the higher interest rate you get, at least for accounts, not for credit cards. High interest rates on credit cards don't do it. But for accounts like savings accounts, if it's a high yield, the higher the interest rate, the more money they'll end up putting in your account as time goes on. Hey, this is a life lesson right now. So take a minute, put the information into the formula, and then stop. That's all I want you to do. So take a minute, put the information into the growth formula, and then stop. Mm-hmm.
Wait, do we just keep the A the A?
Yeah, that's what I would do. All right, so you should already have it in your formula by now. So, for time's sake, we're just going to go through what it looks like. So, my A value, I'm just going to leave it as A. My P, that's how much money I initially put in the account, which I put $7,800 in it, or $7,800. The rate my account is growing at is an interest rate of 6.5%. Now, if you divide that by 100, be careful because it's actually 0.065, not 0.65. 0.65 is 65%. All right, so be careful with that. If you forget that, just take the extra second, do 6.5 divided by 100 in your calculator. It'll tell you exactly what it is. And the time they want past is 29. Now, they want us to find how much money is in there after 29 years to the nearest cent. So it's very, very easy. All you do is take all of this, put it in your calculator, and it should give you a number. Come on. Trust me, guys, if this was college, I'd be able to say some words. All right, now. So here's what it would look like in your regular calculator. So I'm just going to type it in verbatim, making sure that the parentheses are where we wrote them in the formula. So I have 7,800 times 1 plus, you don't even have to do the addition yet, 0.065. And it's going to be raised. So remember, the raised key is that little caret key above the division sign. Raised to the 29th power. Hit enter. Now, that's how much money, if you did not touch that account in 29 years, like you just left it alone, you didn't add or take out any money, that's how much money would be in your account after 29 years. Pretty big from 78 to 48,000, huh? All right. Now, what would this be to the nearest cent? So how many decimal places is cents? It's 100, so 2 decimal places. So if I round this to 2 decimal places, this would be $48,443.25. So after 29 years, I will have $48,434.25, approximately. So A is approximately, because we had to round that. Oh, I switched these. It's 43, not 34. Yes, ma'am. Yes. All right. So try number 8 on your own. So number 8 is very, very similar to what we just did. Put it in the formula, then just throw that in your calculator. So figure out what type it is, whether it's growth or decay. Make sure you put in the correct formula.
So if it doesn't have you know how it has but if it doesn't have your age, do I just leave it?
Like, are you talking about the formula? A is just a placeholder. You can actually put whatever. So, like, when we get later on in the course, we're actually going to be putting numbers in for A and solving for T. But for right now, we're just evaluating.
I feel like letters should not be. You look at calculators.
Yeah.
Wait, what's that mean? Oh, no, yeah, that's not what I calculated. That's that's like an actual calculator.
Where do you even start with that? It's a whole thing. How does it even relate to the alphabet? Does it enter So there's not even a number like alphabet. All of them. I don't want to judge anything, but why should math was you? I was always really good at math. Yeah. So I knew I was going to be good, but my parents aren't. But I was always good at math, and I used that in the world before math. Both of them. I like it. Okay, girl. You like numbers. You have a number. Yeah, I would say, yeah, I grew up in it, so I know all the highs and lows. Okay, there are days where I'm like, me too.
Yes.
Right, she's got the self-control. So me? I don't think I can wait to tell you that he's
I'm going down.
Oh no, they put their hands on me. I don't usually put their hands on me. They're on jail. I'm just trying to All right, so how did I set up my equation? So we have no A value. What's my P? Because that's how many grams we started with. Now, am I doing a growth or decay? Right. It actually says the word decays. So 1 minus, what's 21 points? Guys, please stop talking. What's 21.6% as a decimal? 0.216. And what am I raising it to? The 20th power. And this is one of those cases where it's actually not in years, it's in minutes. But since we're talking about the mass of something, which you will see sometimes. So like if you've taken chemistry, you guys have probably done half-lives with radioactive material. All right, that's essentially what this is. So it's saying that if it decreases at this rate per year or per minute, how much is left after this amount of time? So all you gotta do is just put all of that in your calculator. And what'd you get to the nearest tenth of a gram? Got 1.1 grams. So after 20 minutes, that substance is almost gone. Now, these last couple of problems are actually goes back to the exponential regression. All right. So this is another one. So this is another one where they want us to find the exponential formula, but it has to go through these 2 points. Well, guess what? As long as we have 2 points, that's enough for a table, because all we can do is convert those points into a table. So you just separate the points in terms of x, y. So the first point, 0, 13, what goes under x? What goes under y? And you do the same thing for 8 and 33, 28. Then you put this table into Desmos, and once again do an exponential regression. Yeah, it's all in the OneNote already. It automatically syncs as I do it. You'd be able to watch it now. Yeah. It's like a Google Doc. I mean, you'll still be absent, but sure. So, shh. Really quick, guys, come on. Really quick. I'm going to make this table. Even though it only has 2 points, it still works. So I'm going to type in 0, 13, 8, and then, what was it, 33, 28? I want to hit the little regression key. And I'm going to hit linear, not linear, exponential regression. And there's my function. 13 times 2 to the x power. That's all you got to do. Any questions so far, guys? All right, last thing, and then we're done. Because I just want you guys to be careful with these. So number 11, last one we'll do. Now, don't be alarmed by these, because this is just another way to write a point. All right, because since what we know about functions, don't back up yet. Which of these numbers for f of 3 is equal to 25? Which of these numbers is x? The 3. Because typically you see it as f of x, so x is equal to 3. So what do you think y is? 25. So you still have your chart. So I have y is equal to, or no, sorry, I'm trying to do a table. So xy, I have 325 and then 583. So I'm going to put this in Desmos very quickly. So I have 325, 583. So this is my function. Now, it doesn't want the function. What it wants is that it wants what f of 4.5 is. So once I get the function, I need to find what f of 4.5 is. So in other words, I'm finding when x is equal to 4.5. So guess what? I'm going to type this into Desmos. So type x equals 4.5 into Desmos. Find the point of intersection because the regression automatically graphs the equation graph. In this case, we're using the y value. So, guys, do not pack up unless I tell you to do so. So, x is equal to 4.5. I'm going to zoom out until I see where it crosses the other graph, which is right here. So, if I round that to the nearest tenth, my answer would be approximately 61.5 because you're using the y value. All right, and that's what you would do. So, f of 4.5 is approximately 61.5. All right, so that's it for the review aspect of exponential functions. Monday we'll actually get more deeper into setting up exponential equations. All right, it really has. All right, so your homework for tonight, if there is going to be a new Delta Math, I haven't assigned it yet, but it will be assigned shortly. All right, it's just on this stuff. Hey guys, I actually printed those notes from Delta Math, so your problems will show up exactly like these.
Like, I get it, I'm buzzing.
Make sure you put the tape and your glue sticks up before you leave and clean up around your desks.